Let's wait for 2-3 minutes. After that, I will start. Okay, let me start. Switch off the video right now, right? So this is week 8 regression analysis problem solving session. So today we will be first talking about, of course, the assignment questions. We'll solve the assignment questions of week 7. This is the first thing we will do. Next, we will do some practice questions based on previous concepts. Very few, I think 2-3 is there. 2-3 questions are there. So that thing we will do. And after that, we will thoroughly revise the week 8 contents and necessary practice questions we will do. Okay, so these are the few things we will be doing today. Okay, so in the beginning, let us start with the assignment questions. let's jump to the assignment questions of week 7. So let me, yeah. So these are the assignment questions which are given for week 7. So the first question here is that let EI be the ith ordinary residual. Then which of the following options are correct? So EI is the residual. We know this is the symbol of the residual. Then what is its variance? This B of EI is the variance of EI. So let's do this variance of EI. So it is given that this is question number 1 that EI is the ordinary residual and particularly the ith ordinary residual. So what is the variance of EI? Okay. So this is what we need to find. Okay. So we know that EI, the ith residual, is nothing but Yi minus Yi hat. Whatever it is, be it a multiple linear regression model or a simple linear regression model, you will have the similar definition for the ordinary residual EI. Well, but if you have to write it in the matrix form, then how will you write? It will be Y matrix minus Y hat matrix. This is what your ordinary residual looks like, which consists of all elements. So it will be a kind of a vector. Okay. Now I know that this Y hat can be written as H times Y, right? Because Y hat is equal to HY. This H is a hat matrix, right? We know this from the previous lectures discussion. We know that Y hat is equal to HY. So we can write this. Finally, we can also okay. So finally, we can write this as y into you can write I minus h. Right. So this is your ordinary residual. You can say it a matrix or you can say it is a vector. Okay, because it's a one-dimensional, you can understand. So it can be written like this. The ordinary residual can be written like this. Okay. Now you have to find out variance of E. Let's forget about EI. Let's talk about variance of E. Suppose the entire matrix you want to find. Then what will happen? You know that whenever variance has to be found out of C times some Y, C is some constant, you get the variance as E square variance of Y. Correct? This is known to us. So I minus H is actually a constant quantity. So you can write this I minus H whole square times variance of Y. Correct? So this now I minus H whole square can also be written as I minus H. Why? Because if H square is equal to H, which is hat matrix is an idempotent. If this is an idempotent matrix, if H square is equal to H, which is an idempotent property. If it is an idempotent matrix H, then I minus H whole square is also I minus H. Means I minus H is also idempotent. So this is property. Okay. So I minus H whole square can be reduced to I minus H and finally variance of Y. Therefore, what we can write is that it is nothing but I minus H. Now variance of Y is sigma square. Or you can write variance of EI, ith ordinary residual. Now I minus H will be reduced to 1 minus H, only the diagonal element, HII, not the IJ. Why not IJ? Because IJ is corresponding to the covariance matrix. This variance matrix, it is only the diagonal elements. We have seen that. So this into sigma square. Therefore, variance of the ith residual should be this. This should be the answer. Okay, so variance of EI, so I'm writing it again. This is nothing but sigma square 1 minus HI. Okay, so this is the answer. So if you go back to the question, first question, you will see that the answer is variance of EI is sigma square 1 minus HI. Right? Now, Let's go to the second question. Let EI be the ith press residual. Remember, now EI is not the ordinary residual, it is a press residual. Then what is the variance of EI? Okay, fine, let's go ahead. In question 2, it has been mentioned that your EI is ith press residual. Well, what is the definition of the press residual? We have seen in the last class. Press residual is, we have defined it like this. E of I is equal to EI divided by 1 minus HII. But this is we have defined as the press residual. Okay, we have defined this as the press residual. Fine, and this is the ordinary residual. Right. So, although it has been mentioned here that EI is the press residual, we are writing this as this. Okay, because otherwise there will be a confusion in the symbols and all. So let us write it like this. Fine. Just it's an explanation to yourself. Fine. This is your. Let's do the variance of this. Variance of E of I, the press residual. So variance of press residual is variance of the entire quantity. What is that? EI divided by 1 minus HII. That's all. Correct? So now if you do this, you will get 1 upon 1 minus HII, this whole square into variance of EI. Why? Again, with the same property, that variance of Cy is equal to C square variance of Y. That's the same property we have used because 1 minus HII is a constant quantity. So that's square. Okay, now what is variance of EI? We have just now solved. What is the variance of EI? It is sigma square 1 minus HII, right? Divided by 1 minus HII whole square. So this 1 minus HII and one of this will cancel. So finally we will get this as sigma square upon 1 minus HII. Therefore, the variance of ith press residual. So this is now what? Variance of, let me write, of ith press residual. Okay, this is nothing but this sigma square upon 1 minus HI. Let me just write that we are writing EI as this E of I, so that there is no confusion. So finally, we are getting the variance of the ith press residual is sigma square upon 1 minus HI. So this is actually dependent on simple uh, what I will say statistics or probability. Okay, so you can easily do these questions. Okay, so this is the second question, and we get the answer sigma square upon 1 minus HII. Now, the third question is based on some table where the diagonal elements of HII are given. So, there are 20 observations, and corresponding to that, HIIs are given. Of course, the number of observations, if it is say n, then there will be n diagonal elements of H matrix, F matrix. We have seen that n by n matrix. We know that. Okay. And also, it's a multiple linear regression model given with three regression coefficients or two regressions, x1 and x2, right? And they have 20 observations. Fine. Let's see what are the questions. Given that SS residual is given 109.95, E12 means E12 is the E12th observation. Okay, it's not actually E12, E12. E12 is 3.947, which is also given. Find the value of MS residual approximately. Okay, so what is the reason of giving this E12 here? Nothing, because MS residual always depends on the SS residual and the degree of freedom. So there is no way that this E12 will be useful in this particular question. It may be useful in the next question. Okay, so we have to calculate the MS residual as our question number 3. So let's do it. So in the question 3, it is based on a table which is given, and it has been given that SS residual is 109.95. This is given. Okay, and we need to find out, so to find the MS residual. What is MS residual? We know definition of MS residual, SS residual, divided by the degrees of freedom of SS residual. Well, now, how many degrees of freedom of SS residual? So there are n degrees of freedom because n observations are there. But so degrees of freedom of SS residual. So n degrees of freedom should be there, but there are three constraints. Why? Because of three regressors. Okay, so three regressor coefficients. Sorry, unknown parameters. So n minus 3 will be the degrees of freedom. So 20 minus 3, which is 70. So your M's residual, which is the question number 3, is 109.95, which is the SS residual divided by 70. This gives you about 6.467. This is the answer. Okay. So MS residual does not require E12 value. Fine. So let's go to the question again and let's see what is the answer. Yeah, it is 6.467. Right. Let's go to the question number 4. Question number 4 says, consider the data in problem 3. The 12th standardized residual, D12, is approximately equal to. So we need to find out the standardized residual. Okay. So for standardized residual, what we require? Let's see. So to find standardized residual, okay, to find standardized residual and 12, right, D12. How to write the standardized residual is E12 divided by root over only MS residual, right? This is the standardized residual. DI is equal to EI divided by root over MS residual. This is your uh, what you call as the standardized residual definition. So D12 will be E12 upon this. Now, given in problem 3 that E12 is how much? 3.947. So it's 3.947. And MS residual we have already found out, that is, which will not change, 6.467. Right? Based on that, we can easily calculate B12, which is E12 3.947 divided by root over 6.467. What is that? It comes out to be about 3.947. Let me give you the value of root over MS residual, 2.543. This gives you 1.552. This is the answer. So 12th standardized residual is 1.552. Okay, so let's go to the question again. Problem number 4, 1.552 is the accepted answer. Fine. Now next question is 12th. Now it is a, they have given it as a standardized residual, but it will be studentized residual, I guess. So because R12 is given. Okay, so it is not standardized, it is studentized residual. Okay, so let's do it. Question number 5 is to find out studentized residual 12th one. So R12 studentized residual. And what is the definition of that? It will be E12 divided by root over MS residual. There will be no change, but with 1 minus H II, that is 12, 12. Okay, don't confuse, it is 12, 12 because Ri studentized residual is EI divided by root over NS residual into 1 minus HI. Okay, instead of I am writing 12, 12. Okay, that's the thing. So almost everything is known. H1212 is given in the question is 0.178 from the table in question. Okay, so 0.178. And finally, therefore, R12 studentized residual is 3.947. This E12 is also given, divided by NS residual we have already found out, 467 into 1 minus 0.178. Right? So R12 finally will be 3.947. Let me give you the value of the root. This will come out to be 2.3056. Finally, the answer comes out to be 1.712. This is the answer. Okay. So 1.712 is the your studentized residual. So one thing you can check here. that this 1.552 is the standardized residual and studentized residual is 1.712. So not much difference between R12 and T12. And we know that as a criteria to look the outlier point like leverage point or influential point, this difference should be very, very large. But here it is not there. So it is clear that the 12th residual is not very far away when you calculate the studentized as well as standardized residual. Okay, so let's go to the question. Yeah, 1.71. So it's fine. Next is consider the data in the problem 3. Which of the following is most likely to be an outlying observation with respect to its x values? Outlying observations with respect to its x values represents the leverage point, right? Because leverage point is that where your x coordinate is unusual. So we need to find out the leverage point. And we have seen most of the times that leverage point depends on the HII, right? So question number, I think, 6. Leverage point is nothing but outlier with respect to x coordinate, right? Because it has unusual x coordinate. We are seeing that today also we will discuss x coordinate. Okay. So, and we know that this kind of point, leverage point, is that point where you find that your what you call as this HII is very large, right? So that 1 upon 1 minus HII, this 1 minus HII becomes, because since the HII is very large, 1 minus HII tends to become very small. And therefore, this statistic, this 1 upon 1 minus HI, will tend to a large quantity, right? So, yeah. So this will tend to be a very large quantity. That's why we can call that as a leverage point. And if you just look into the observations of HII, you will find out that the third observation is the strongest, 0.372 is very large. Okay, we will see in this today's uh, this session that there is criteria to see the leverage point. But for the time being, if you have to look at and compare all these observations, then you can say that whichever has the strongest value of HII in these options, that option is the correct option for the leverage point. So here observation 3 is very large. In fact, you can see that observation 15 is also very strong, 0.333. Huh? So that will also be a can be a leverage point, but here we need one value, one observation. So of course, the highest HII value will be the correct option. Okay, so this is done. Sixth one. Now seventh one is that same data E12 means the fresh residual has to be found out. Let's see. Okay, so here observation 3 is the correct option. Let's go to question number 7. We need to find out E of 12. That is fresh residual. 12 fresh residual. And there is a clear cut formula for this to calculate. So no need to do manually everything. So it is E12 divided by 1 minus HII. So it will be in place of II, it will be H12. Correct? This is the thing. And we know that E12 is given to be 3.947 and the denominator is 1 minus 0.178. Finally, 3.947, and if you calculate 1 minus 0.178, it will be 0.822, right? So finally, the answer will come out to be 4.801. This should be the answer for the this residual, right? So if you go to the question again, this residual is 4.801. And the last question is press, this residual, substantially larger than SS residual indicates what? So for that, let me just show this one plot. This is question number 8 about the press residual and SS residual. So let us draw a graph that will be the best. Okay. Suppose I have some arbitrary points here, and one point is somewhat unusual. Okay. So now, if you don't use this point, okay, let the coordinate of this be xi. This is x, this is y, okay, and this coordinate is yi, right? And if you don't include this xi yi point, this point A, if you don't include and do a regression, then you will get a trend line like this, or slope or intercept you can calculate. This is like this. Suppose, okay. So corresponding to this same xi, you are getting when this ith point is not used, you are getting your response, fitted response as y hat like this. Okay. Now, if you are including this, then you might get, and change the color, you might get a trend line like this, right? Here, this point is your y I, right? So now this is where the entire thing is. This difference between yi and yi hat, this difference is what you call as the SS residual. And this difference, this bigger difference with yi and yi in bracket I hat is your the press residual, right? Because the press residual's definition is like that. If you ignore ith value, then what is the difference between yi hat and yi? That is your press residual, correct? So if your press residual is much greater than SS residual, you can see that your fitting is much better. So fitting of the model is much better, right? Model is much better. So if you go to this question, press substantially larger than SS residual, which I have shown, that means the fitted model is likely to predict the new observation well. Okay, if it is very near to the SS residual, then it is not very well. Okay, so that is the biggest thing, right? So, oh, I'm sorry. So the fitted model is not likely to. Sorry, sir. The fitted model is not likely to predict well. I'm sorry, because the fitted model means this one. This one they are talking about this, right? Because you have to include this point also. Because entire data you cannot neglect any particular data. Okay, so fitted model is much better if you if this ith observation is removed. Okay, so press is greater than SS residual means that the fitting or the fitted model is not likely to predict new observation well, right? Because there is an error, you can clearly see that because of the inclusion of this point, right? So this is the last question. So with this, our assignment part is over. Now we will do some few questions based on the previous or some very basic questions. After that, we will move to the 8th week contents. Okay, so let me just quickly write one or two questions. These are all included in the practice questions of I think week 8 only, but really not related to the week 8 content. That's why I just wanted to show this. So the question is, these are some practice questions. So first question is, suppose let y be the vector of response values and e be the vector of residuals. We know that. Okay, this is the symbols we know. Residuals. Okay. Now they ask e dash y will be equal to what? Okay. So I'm not giving the options in the question. If you look at, you will find several options. So let us try this. Okay. Easy. Let us try this. Okay. We already know that e is nothing but I minus h times y. This we know. We have seen it. Okay, this is I minus h y. Why? From where it is coming? From y minus y. And y hat is h y. From this it is coming. Okay. Now if you say e dash, this will be what? Just e transpose, right? E minus h dash. And e dash y will be this I minus h y transpose y. So if you just do this, it will be y dash I minus h dash into y. What I do is that next is I multiply with I minus h in between. This I can do only because this I minus h is an idempotent matrix. So this will ultimately give you I minus h whole square, right? So if this is happening, if this is true, then uh, means this I minus h square is actually equal to I minus h because it's an idempotent property exists. That's why you can multiply here. Otherwise, you cannot. Okay. So this is what you get. So finally, you will get y dash as into I minus h dash, whichever I have written in the last step. So I have made this intentionally to show that this is nothing but the idempotent property. And finally, you will get this is as e dash and this is e. Right? This is E and this is E dash. So E dash Y is nothing but this. And what is this? This is SS residual. And what is SS residual? We know R square is equal to SS regression divided by SS total, or you can say 1 minus SS residual by SS total. Okay, so actually the options are in terms of R square. That's why I'm writing like this. So it will be 1 minus R square into SS total is nothing but SS residual. Therefore, E transpose Y or EY, if you have to say, that is nothing but 1 minus R square into SS total. That's all. Okay. Only one step is important here, that I can multiply this I minus H with this in the middle. Okay. Because of this property. Fine. So this is what you have. In fact, if you don't have this E dash also, you will get this same. Fine. This is one of the questions I wanted to show. Another is very easy. It is actually not related to this. So suppose we fit y is equal to beta naught plus epsilon. So no regressors. What is R square? They have asked what is R square. No regressors. So what is the coefficient of multiple determination R square? So what is R square? No regressors are there. So no regressors means what? Your SS regression will be 0. And what is R square? Is nothing but SS regression divided by SS total. Then what is this? 0. So R square will be 0 corresponding to a no regressor model. And actually from here only we got that thing that 1 minus SS residual divided by SS total So if R square is 0, so we get SS residual is equal to SS total. That's why, remember when we were doing that partial F tests and all, we have always taken SS total is equal to SS residual corresponding to a no regressor model, right? So this is one of the earlier part. And another question based on the previous uh, week's content, that is simple question, that what does normal probability plot means? So what it is for? So probability plot. So we know that this normal probability plot is to test whether epsilon is actually following a normal 0 sigma square distribution or not. So to test normality of errors, this is the error term, so errors, or you can say the residues. That's the thing. So normal probability plot, where we have seen that over what you call as heavy tailed, light tailed, or ideal case, that is particularly to test whether this epsilon is actually following this normal distribution or not. That is the main thing. Okay, so these are few questions which are based on simple concepts, not related to the week 8 context. So now I will go to the week 8 contents, and very few questions are there and very simple questions are there, which you will get in the assignments also. Very similar questions. So that's the thing. Let me now start the week 8 content. Okay. So, right. So just a minute. So in the week 8, we will the first part of the week 8 module is based on similar, that is model adequacy checking, and we will get some more insights on how to test whether any point in the data set is a leverage point or it's an influential point. We'll get some tests, okay, so that we can identify whether there is a leverage point present or there is some influential observation present or not. So I will start with the basic definition again of the leverage point and the influential observation, and then we'll write all the steps which are also discussed in the NPTEL module. So I will discuss it again, and with that, along with that, we will do some practice questions. And practice questions, as we will see, that it will be very simple and easy. Fine. So let's do it. So let's start with the concept of leverage. Okay. So you have X, you have Y, and you have some data which is mostly scattered up to this point. Okay. And you have a corresponding trend line like this. And one of the points is somewhere here, which might be over the trend line or near the trend line. It does not matter. But it has some unusual x coordinate. See, there is a huge distance in the x direction from these data points, right? So this is unusual x coordinate, you can see. This is the important observation, that is the unusual x coordinate. This A point has unusual x coordinate. This point, this A, this point, we call it as a leverage point. Okay, so this is a leverage point. Now, how to test for a leverage point? We have seen so many things, so many graphs in the last section, which are very confusing and very, but These also are an important things like what we have studied, like the studentized residuals, then what you call as standardized residual, press residuals. All these things are also very important, very important for understanding. And graphs are always good. But is there any test through some mathematical viewpoint? It is there. So we will see those. Okay. So let's discuss about the tests for identifying leverage point. Right? So let's again assume a multiple linear regression model. So y is equal to in matrix term x beta plus epsilon, correct? And we know that when you fit the model, you have the unbiased estimator for beta hat as x prime x inverse x prime y. This is your beta. We know that we have derived long ago. Now the fitted model, therefore, the fitted model is what? Y hat is equal to x beta hat. Correct? So y hat is equal to x. So beta hat will be what? Just put the expression which we have derived here. X prime x inverse x prime y. Okay? So this can be written as h times y, where h is nothing but x, x prime x inverse x prime. This is your hat matrix, because it maps, this matrix maps the elements of y to the y hat. Okay, so this is your hat matrix. We have seen it in detail in the last class, but again, let us do it one by one. So this is your hat matrix, which plays a vital role in finding the leverage point. We have seen it also, that 1 upon 1 minus HII. HII, as it increases more and more, your 1 upon 1 minus HII, it also becomes large. And that produces the identification of the leverage point. We have seen that. So, vital role in finding or detecting the leverage point. Okay. This is an important parameter. Now, x n by k, which is a matrix, can be written as like this: x1 prime, x2 prime, so on up to xn prime. So it's a n by k matrix. You can understand that these are n observations, and this x1 dash will consist of all regressors, right? You know that this x1 dash will be a row matrix. You can see, okay, with k elements. Fine. Now this HII from this matrix only, HII can therefore be written as xi prime. This will be remaining the same because it's a k by k matrix, and this will be xi, the prime of it. Okay, so this is your HII. If you want to find out the diagonal element, then you can write it like this. This HII is a standardized measure of distance of the ith observation from the center of the x coordinate. Okay, so this is an important parameter. Therefore, okay, this thing will not change because I have told you that is a k by k matrix. Only thing which change is this I dash and I. Why? Because this is related to the ith observation, and we are finding out HII. Remember that this H matrix is nothing but n by n matrix. And this x has this n by k, this has k by n. So the observation is actually related here, but x prime x inverse is the k by k matrix. So no observation part is present in this x prime x inverse. You can understand it that way, this way. Okay, so this is the point which I wanted to make. Now Okay, we have suppose calculated HII based on whatever way. You can do it in this way or you can do it in this way, whatever way. And we have also calculated in the last time that in the practice question we have calculated the H matrix. Fine. So you have HII values. Now, criteria is that if your HII is large, then ith point is the leverage point. We have seen that. But we don't know the proper criteria. How large is that large where we will consider that to be a leverage point. Okay. For that, now how large? How much large you have to be? So how much large the HII should be to call it a leverage point, right? We don't have that criteria. In the assignment question also, I was talking about that HII should be large, and we have found that there is one largest value is there. That observation should be the leverage point. That is correct, no doubt. But up to what extent I can call that no, it is not a leverage point, but after that I can call that as a leverage point. That is what is missing right now. So there is a criteria that is H bar, which is nothing but adding all the observations of HII means adding all the diagonal elements divided by n. Okay, so it's a mean kind of a criteria. So all the diagonal elements addition means nothing but trace of H divided by n. Sometimes this is also called as rank of H divided by n. Or finally, it can be called as K by n, where K is the number of unknown parameters or regression coefficients. How many regression coefficients are there in this beta naught plus beta 1x 1 plus beta 2x 2? So if you have this model, how many number of regression coefficients? 1, 2, 3. There are three unknown parameters of three regression coefficients. Remember this. Okay, regression coefficients, not the number of regressors. Fine. So this is your K. Now the criteria to call something as some point as a leverage point is that your HII should be greater than 2 into K by N. Okay. So this indicates if this criteria follows, this indicates that ith observation is a leverage observation or leverage point. Okay. This is the criteria for understanding the leverage point. Fine. So this is the we have calculated the H part which is equal to, let's go to this, K by N, where N is the number of observation and K is the number of regression coefficients. And criteria is that HII should be greater than 2K by N. Okay. So once we have finished this, let me do a question, practice question. It is there in the, I think, in the practice part in Week8. So let us do one question here. Okay. So question is that observation observation 5 and 15 and outline observation in terms of its x value. In terms of its x value. Okay. So they are talking about observation 5 and 15. Of which question? The question which we have seen in the week 7 assignment. Okay. So just look at this question and try to understand that they are asking for whether this observation 5th and 15th an outlying observation in terms of its x value. In terms of its x value, this statement tells you that you have to understand the leverage observation. Okay, you have to find out the leverage observation, whether it is the fifth one is the leverage point or the 15th is the leverage point. You have to check. Okay, so I'm giving you the age values. Don't worry. So this is related to table in week 7 as well. Okay, so if you look at the fifth 5 5, okay, age fifth observation, so fifth observation, you find that age 5 5 is 0.248. Let me check it also once more. Just a minute. So this is actually corresponding to this table. See, the fifth observation is 0.248. Let me check the 15th one, 0.333. Okay, let's go ahead. So fifth observation is 0.248. Okay, let's check whether the fifth observation is a leverage point or not. So for that, what is the criteria? You have to calculate h bar. What is h bar? K by n. And it is given in the question that it is given that y is equal to beta naught plus beta 1 x1 plus beta 2 x2 plus epsilon. Okay, so for this kind of a model, what is your you have to check whether 5 observation 5 or observation 15 is a leverage point or not. So if this is the model, then we have k is equal to what? 3, because we have 3 unknown parameters or 3 regression coefficients. So it will be 3 divided by n is 20. Okay, so this is your h bar. So h bar comes out to be 3 by 20, which is 0.15. Okay, h bar is equal to 0.15. This will not change for entire set of observation. This will not change because this k by n will depend on this and the number of observation. So h bar is fixed. Now, what is the criteria? So the criteria for leverage point is that it should be greater than 2 times h bar. So h bar. So 2 times h bar is zero point 0.3. Now check h55, which is 0.248. Is it greater than 0.30? No, it is less than 0.30. Therefore, it is not a leverage point. Correct? And what about the other one? H15, which is 0.333. This is greater than 0.30, which means that it is a leverage point. Clear? So through this, we can understand that yes, this is the leverage point. Fine. So this is a question to check whether any observation is a leverage point or not. What we require is that if you have been given the age tables, which will be given, you just need to see what is the regression model they have used. From there, you can calculate K and what is the number of observation given in the question. So that is 20. So based on that, you can easily calculate the H bar. 2 times H bar is the critical limit. That's all. Okay. So this completes the test for the leverage point. Fine. Let's go to now the influential observation test. So let's go to influential observation. Influential observation. So what is influential observation? Unlike the leverage point, if I again draw a graph, This is X, this is Y, and these are some points. Again, just like what we have drawn, and it is mostly scattered here. And A is the point which is somewhere here. So it has no doubt an unusual X coordinate as well as Y coordinate. So this is A. So unusual X and Y coordinate, right? And this is the A point is the influential observation. And this influential observation, these point significantly affect or significantly it has an effect on regression coefficient. So that's why there is a coefficient related test also. Okay, so let us go one by one. What are the different tests for influential observation? The first one is the Cook statistics. Okay, Cook's statistic. Okay, so what is this Cook statistic? It is defined as D. Actually, this Cook statistic is symbolized as D, which is distance. Let me write and then I will show distance between predicted response y hat obtained using all the observation and predicted response y in bracket I hat obtained without ith observation. Okay, so let us understand this. So suppose you have these observations. This is x, this is y, and these are some scatters. Okay, and you have a influential point over here, which is a. And if you don't use a, then this is the trend line. If you use a, then this is the trend line. Correct? So here, let us say that this is xi, this is yi for this point. Corresponding to same xi, the predicted response is yi when all the points are included, including a. But when this a point is not included, then this is the trend line. But for this same xi, the predicted response is y hat in absence of I. So this is the yi hat. So the distance between these two is what you call as the Cook statistic. But this is the Euclidean distance. So this is defined as di is equal to, you can see this is yi hat minus yi hat dash into yi hat minus y hat divided by, okay, so this we can remove because it's a matrix kind of a thing, divided by k. Same, k is the number of regressor coefficients, and then is receiver. This is how the DIs are defined. So as you can see, this is d of I. So for each and every observation, you have to calculate. So if there are 20 observations, then you will have 20 values of DI. Correct? And in each of this, one of the observations has to be removed. So let me make it more clear. Let us say that you have, suppose, this is suppose x, this is suppose y, and there are some five observations: one, two, three, four, and five. Okay, there are five observations which are present. So let me write one, two, three, four, and five. Okay, so there will be five d values or Cook statistic. Okay, so for this is your x1, this is your y1. So the first step is that suppose you are calculating d1. Okay, so d1 means what? D1 means you need same graph you draw. Okay, and this is the second point. Suppose this is the third point, this is the fourth point, and this is the fifth point. 2, 3, 4, 5. And this is x, this is y. And this is your x1. But you don't have the first point right now. Okay. Based on this, if you draw a regression line, which will come out something like this, suppose. Okay. Corresponding to x1 will get a value of y1, which is y1, this, the bracketed one. When one's first observation is not present, if you in excluding the first observation, all other observation you include and draw a trend line, whatever the response you will get, the fitted response, that is this y1 bracketed 5. Okay, this minus when you have all the observations, then you might have something like this. I don't know. Okay, so corresponding to that, this is y1 hat. These difference, this y1 hat and this y1 actual hat, this difference is being used to calculate the B statistics. Okay, so let me again write. So di is summation of I is equal to 1 to n. So it will be yi minus yi whole square divided by k into ms residue. Okay, this is how it has to be found out. So for the D1 case, what you will write? So yeah, so this will be y1 of that minus y1 whole square divided by k into ms. Okay, so this is how you have to find out. Well, so the rule is di is much has to be much larger than other values. So you will calculate d1, d2, d3, d4 like that. Whichever is the largest is the influential observation. That is the influential observation. Okay, so this is the criteria. Fine. So let's check any other criteria. Most of the questions you will not get from this B statistic, the Cook statistic, but these now next whatever the things are coming, those are important. Like BF fits. Okay, this is means difference between fit statistic. Difference between fits. This is the statistic. Now how to represent it? In a similar way, you can represent. So let me just define. So for ith observation, this statistic is defined as, so DF fits ith is nothing but yi hat minus y in the absence of the ith point hat divided by root over ms residual in the absence of ith point into h I I. Okay, so this is your df fix. So as you know, this y hat of bracketed I means fitted response of yi obtained without use of ith observation. So again, if I draw this, it will be clear. One is this, one is this. Okay. So in one case, you have one, two, three, say let's say 4 points. And this case, you have two, three, four. Okay. So based on this, this is your profile. And let me draw the same profile here. But based on these 3 points, let it be like this. Okay. So this is the first, second, third, and fourth. This is second, third, and fourth. Corresponding to x1, this is your y1, and this is your y1. Now, same corresponding to x1 here, your y1 hat is this, but this is in the absence of 1, right? Now, this case, for this case, when 1 is not present, the first observation is not present. So here 1 not present, and here 1 is present. Okay. In this case, you calculate MS residual. So then that will be nothing but MS residual of 1. Correct? And HII you can always calculate based on the observations. So this will not change whether one is present or not. This will be always the similar. Okay, so this is the thing. Now, what I will do is that I have this y1 hat value, I have this y bracketed 1 hat value. So I will write df fits of 1 is y1 hat minus y bracketed 1 hat divided by root over ms residual of this case, that is of 1 into h11. That's all. Okay, so this is the first. Similarly, for the second, you have to remove the second and like that. Okay, so as you can see, there are suppose n observations. So suppose you have n observations. So how many df fits value will be there? There will be n df fits values. Right? This is important. We'll get most of the questions from this kind of a thing. Okay, so this is your DF fits. In terms of matrix, also we can write. So DF fits. These are different definition using matrix form. So y hat A minus y hat bracketed A divided by root over ms residual of bracketed A into h hat. Now, which one is higher? You can say that the rule is this df, I have given a mod here, df fits I should be greater than 2 times k by n to the power half. Same, k is number of regressors or number of regressor coefficients, sorry, regressor coefficients, coef, and n is total number of observations. Right? So this is your df fits. Now, corresponding to this, there is one question which is very simple question. Let me just see where I get it or not. Yeah, very easy and simple question. Let me put it. So suppose you have given that y is equal to beta naught plus beta 1 x1 plus beta 2 x2 plus xi. And suppose there are 20 observations. Okay. Now in order to identify possible influential observation, the total number of DF fits to be computed is. So we have discussed this. So how much it will be? So if there are 20 observations, then there will be 20 values. Correct? Because DF fits depends on only I. So each and every time you have to remove one and try to calculate the DF fit value. Okay? So there will be, the answer is, there will be 20 values because the number of observation is that of DF fits. Needs to be computed. Okay. So this is the simple question, as you can see. We have discussed it. Right. So based on that, you can answer. Fine. Similarly, you have another test for influential observation, that is DF beta. This is also important. DF betas. So betas, you can understand that these are the difference between the regression coefficients. Difference between betas. Okay. So the definition of this is, let me just quickly write, how much the regression coefficient beta j hat changes if ith observation is deleted. Same way, everything is same, but with different parameters they are doing. So how to define therefore? Df betas ij. Now there will be I observation and j regressors. So I observation, j regressor or regression coefficient. Regression coefficient. So it can be beta 0 or 0, 1, and 2 or 3, whatever you have to do. Fine. So this will be beta j hat minus beta j with one of the observations deleted, divided by, say, root over ms residual of I into, now this is the change, x prime x inverse jj element. Okay, because this x prime x inverse, if you remember, I have already told you, x prime x inverse is a k by k matrix. It depends on the regression coefficients. Okay, so the jj, the diagonal elements of that has to be used. Okay, so this is the how it is defined. Okay, where, just let me write completely, beta j of I, this symbol is the jth regression coefficient. Remember, regression coefficient, don't use only beta 1 beta 2 because 0 is also there. Okay, coefficient computed without use of ith observation. Okay, so you can see bracketed I represents that. Again, for this, the rule is df betas ij, its mod is greater than 2 by root n. This is the criteria. Okay, so this is the another test for the influential observations. Fine. And when will you discard any influential observation? Suppose you have some observation, like suppose you are saying that sea surface temperature and rainfall. Okay, and you have all kinds of observation like this. Okay, as sea surface temperature increases, rainfall is increasing. Suppose. Okay, One of the observations you get here, will you discard this observation because it will be an influential observation because it has unusual x and y. Will you discard this? No. It will be discarded, this point will be discarded only when there is an observation error. You are doing some practical experiment, if there is an observation error, then only you can discard. Otherwise, you cannot discard because there is no logic behind discarding. Discard any influential observation. That's all. Fine. So this is all. There is a question related to this. One of the, I think this is the last practice question which is there because as you can see, these are all simple questions. After that, only some theories are there. Let me just write. So again, just like the previous one, in order to identify possible influential observations, the total number of DF bitters computed. So how many? Is it equal to the number of observations or is it more than that? So just look into it. DF bitters is in I and J. So there will be, suppose let me write here. Suppose you have, so it is given, suppose in the question, that it is y follows beta naught plus beta 1 x1 plus beta 2 x2 plus etc. Okay, this is your y, and suppose n is equal to 20. Then how many? Okay, so here it is given that there are three regression coefficient, three regression coefficient. What are they? Beta naught, beta 1, and beta 2. So J will be 0, 1, and 2. So there are three regressor coefficients which are present. And how many observations? N is equal to 20. So 20 observations present. Remember, these DF betas, this depends on both I and T. So depends on both observation and regression coefficients. Correct? So if you have like this, then you will have n by k or n into k. So it will be 20 into 3, that is 60 times it has to be computed. The beta has to be computed 60 times, right? So number of regressors increases, you have to just multiply. That many times you have to compute. Okay, so these are some basic conceptual questions which are there. I think that's enough. These are the questions which you will find in the assignments. It's easy. You can easily get it. Okay. So this completes, I think, the influential observation. There is another statistic which we just, since it is given, I just mention, and then finish with model adequacy checking, and then we'll go for the transformations. Okay. So another is the fourth one is the press statistic. So the press statistic is higher press residual, we know is this EI, which is YI minus YI hat. Correct. So it is actually defined as, the statistic is defined as summation of E bracketed I square. I going from 1 to n. This is summation YI minus Y bracketed I hat whole square. So this becomes summation EI divided by 1 minus HII square. That's all. Okay. So every time You have to compute this, square it, and sum it. That's the thing. This is similar to that of the summation which you get for the B statistic, right? Cook statistic. There is this summation is there. So I think this will not be there, right? So that's all. That is the your model adequacy check. How to check the leverage point or the inferential observation. Fine. Now, next is the next module, which is transformations and weighting to correct model inadequacies. So, transformations. Now, suppose you have some leverage point or some the error is large or the residuals are large, then what transformations you can make? So, transformations and weighting to correct model inadequacies. Okay. So, suppose you have xi, yi, one of the points where I can go from 1 to n, and suppose it's just a simple linear regression model, beta 1 hat x. Okay, so what is your ei? We know it is yi minus yi hat. Simple. These are the ith residual. This is ordinary residual, people can say. Okay, but I am writing ith residual. We have seen in the last lecture that residual plot is how to plot it. It is actually in EI versus YI, right? Not with YI because EI and YI shares the linear relationship. There is discussion there. Okay. So the first is that in the residual plot, if you remember, this is your YI hat, this is your EI, and this is EI is equal to 0. And if your observations are staying like this in a band, then it is said that it is a satisfactory model. We have seen all these things. And the variance of epsilon is actually sigma square, which we want, right? Because we have assumed that epsilon is uh, normal 0, comma sigma square. We have assumed for simple linear regression or multiple linear regression model. If this is true, then our assumption is correct. Well, now, if it is not true, let's go ahead with when it is not true. We have seen it also, but still let me show it. When it is not true, this is EI equal to 0. Sometimes happens that the model is like this. So all the observations are growing like this. In this case, this is an unsatisfactory model. You can see that variations of epsilon I, it increases as yi increases. Okay, so this is yi hat on this. Similarly, opposite can also happen like this. So this is yi hat, this is your ei, this is your ei equal to 0, and it can happen like this also. So observations are like decreasing like this. So in this case, variance of epsilon I decreases as yi increases. Okay, and in both these cases, your variance of epsilon I is not equal to sigma square. Here, that assumption of epsilon normal 0 sigma square is violated. So these are unsatisfactory models. There are many other models like double bow structure and all. So let us just quickly draw it. So this is a double bow structure. You can see these observations are like this, or the residual versus this plot looks like this. Okay. So in this case, double bow pattern, this occurs when y is in proportion between 0 and 1. Again, here the variance of epsilon I is not equal to sigma square. And the last one, for the nonlinear part. If nonlinearity exists, then this is how the observations looks like. Okay, it's kind of a curvilinear band. You can see I is equal to 0, and this is y. So here non-linear relationship. Okay, so in all the last couple of cases, the variance of epsilon I will not be equal to sigma square. Fine. So if this kind of cases exists, then what stabilization or the transformation which we can do to correct the model? So for that, we go ahead with what you call as variance stabilizing transformations. Okay, variance stabilizing transformations. So here what happens is that we have a constant assumption that V epsilon is sigma square, which is constant. So this is a constant variance assumption. And we do entire simple linear regression or multiple linear regression based on this assumption. But if the constant variance assumption is violated, like in the residual plot we see constant variance assumption is violated, so the response variable y will not follow will not follow normal distribution. So this is the problem which occurs if variance of epsilon is not equal to sigma square. Okay, so this is the problem, right? Now, what we can do is that in this, we have some examples like it has been shown that suppose y is not following normal distribution in this kind of a case where constant variance assumption is violated. So suppose y is showing Poisson distribution. Okay, Poisson distribution is something like this. Yeah, so lambda to the power y e to the power minus lambda divided by y factorial. This is your f y of y. Okay, so this is your PDF kind of a thing. So it's a Poisson distribution having parameter lambda, where lambda is actually the expected value of y. So the mean is lambda, and the variance is also lambda. So variance of y is also lambda. If you remember the Poisson distribution, this is how it happens. Okay. In this case, if we reduce this y dash as root over y, if you transform the y dash as root of y, then then you regress y dash with x, then your variance of root y is independent of the mean lambda. Okay. So if you do this, you will find out that the variance of this y dash, which is root y, is independent of the mean lambda. Okay. Because of this dependence of this lambda in the variance, you get this kind of a Poisson distribution, not the normal distribution. Okay. So this is what one of the cases. Second case is when double bow structure comes, that is y is in proportion. Y is in proportion between 0 and 1. So the double bow kind of structure. Okay. So in that case, you take y dash as sine inverse root y, and then you regress. you will find that the variance of y dash is independent of mu, or is a constant kind of a thing of the expected value of y. So these are the things. So there is a generalized expression, and we will do that for a function if the variance is a function of mu, that is the mean. Okay, then what we can do? So let us say for that, let us take some generalized expression. So suppose y has a mean mu and variance sigma square. Okay, so let us say that variance sigma square is not constant and sigma square is a function of mu. Suppose, okay, so variance of the response variable depends on mean mu. Okay, so let us say that u is equal to f of y. Now, why am I doing it? Is that so? We will do here. You will understand why am I doing it. You will use the Taylor series expansion. This Taylor series expansion has to be done about some parameter, right? So about mu, we will do the Taylor series expansion, or about let's say a. Then what happens? So suppose f of yeah, so f of y. Let us do it in terms of mu about the mean. So f of y will be f of mu plus f dash mu divided by 1 factorial y minus mu and so on. But we'll neglect the higher order terms and just keep the first two terms. So based on that, we get variance of u is equal to what? Variance of fy, correct? So variance of fy can be written as what? This is a constant, right? F of mu is a constant. Variance of ay plus b is nothing but a square variance of 1. This has to be remembered. Variance of a constant quantity is 0. Of course, you see, if this is y, this is x, if it is constant, is there any variability? No. So it is 0. So this is a constant quantity. Therefore, this will be 0. And this will be a square of that. F dash mu square into variance of again y minus mu. Again, so f dash mu whole square as it is. Variance of y minus mu. Mu is a constant, so it will be variance of y. Okay. Now this is f dash mu whole square. Variance of y. Now variance of y can I write as sigma square? No. It will be a function of mu. Sigma square is a constant quantity, but here we have assumed that variance of y is not constant. It's a function of mu. We have written this. Now, if we choose a function f such that f dash of mu whole square is actually 1 upon g mu, then f dash mu can be written as then what? 1 upon root g mu, correct? And so the variance of u will be what? I have written what? F mu square is 1 upon g mu. So variance of u will be what? 1. If this is true, if this is true, then this will be true. Variance of u is a constant, okay? Or variance of fy will be a constant, which is 1. Okay, so this is what the thing is. So therefore, now if sigma square is of the order of k mu to the power q. Okay, if this is a generalized sigma square, which is a function of mu, you can see, then g of mu is what? K into mu to the power q. So f dash y will be, say, suppose g of y to the power minus half. From this, we were writing f dash mu is equal to 1 over root over g mu. Instead of mu, we were writing y. That's all. Okay. So therefore, f dash y is nothing but y to the power minus q by 2. Right? Now, therefore, f of y, if you integrate it, it will give you 1 minus q by 2. This will be only when q is not equal to 2. But if q is equal to 2, it will be log 1. Because just put it here, 2. So 2 by 2 is 1, 1 minus 1 is 0. So it will be a log y quantity. Okay. Just put in. So let us look at it. Q is equal to 2. So suppose f dash y, I'm telling that if q is equal to 2, so y minus 2 by 2, which is 1 by y. Therefore, f y will be what? Will be log y. That's all. Integration of 1 by y. So these are the two functions which you are getting. Okay. So let me write it again. So if you are having sigma square as k q to the k mu to the power q, then f of y is proportional to y to the power 1 minus q by 2 or log of y. This is when q is not equal to 2. This is q in equal to 2. That's all. Okay. So based on this, we have certain expressions that let me show. Let me list all those. It is already listed there in the lecture notes. So this is sigma square. Suppose it is equal to constant. So constant means mu to the power 0. So sigma square is constant means that you don't need anything. So no transformation is required. That is absolutely fine. Problem occurs when the variance is not constant. So sigma square now, if it is proportional to p of y, that is, it is proportional to the mu, the mean, then it will be f of y will be equal to root y. This is the transformation we have to do. Okay. Third, if sigma square is proportional to ey whole square, u square, then your f of y will be equal to log y because q is equal to 2. This is corresponding to q is equal to 2. Fourth part, if sigma square is proportional to e y whole cube, then f of y is proportional to y to the power minus 1. Just put it in this, you will get it. So it's 1 minus 3 by 2. So it will be minus half. Okay. Fifth, if sigma square, let's go ahead, e y to the power 4, then f of y will be what? Let's go ahead here. So 4 by 2 is 2, so y to the power minus 1. Okay. So in this way, you can proceed. And another is the sigma square. If it is like this, that it is ey into 1 minus ey, this kind of case, if happens, then you have to use f of y as sine inverse root y. This is that proportional case. And this one is the Poisson case. Okay. So these are some lists of the transformation. And there are some transformation to linearize the model. Let's do those and finish today. Okay. So the last part of today's is the transformations to linearize a model. Sometimes what happens is that always when you get some data between x and y, you plot a scatter plot. Okay. You just have a scatter plot. And suppose your scatter plot shows a kind of an exponential distribution, whether it is exponentially growing or suppose this kind of a scatter plot you are getting. So you are getting some kind of an exponential fit between x and y. Okay, either exponential growth in this case or exponential decay. Anything can be possible. So some suppose like this. Okay, so this is x, this is y. So exponential growth or decay, if you get, that means y is equal to beta naught e to the power beta 1 x. If this is what your uh, fitting comes, then you can transform it into linearized form. How to do it? If you take a log y, then this will be log of beta naught e to the power beta 1 x, right? Log of a into b is what? Log a plus log b. So this is log beta naught plus log of e to the power beta 1 x. So this will be log of beta naught plus log and exponential are opposite and will cancel with this. So your y dash will be equal to beta 1 x plus some beta naught dash. Okay. So if you now do a fitting between x and log y, you do a simple linear regression model, whatever intercept you get is nothing but beta naught dash, which is log beta naught, and slope which you get is nothing but beta 1. That's all. Okay, this is one of the cases. Second case is that when you have some kind of a fitting like this between x and y, as some like this, sometimes this, and somewhere this. So this is these are beta 1 greater than 1, beta 1 equal to 1, and beta 1 less than 1. So actually, if your fit is like this, x to the power beta 1, you get a relation like this. Okay. Then again, you can take some log to linearize. This is log beta naught plus beta 1 log x. Right. So now your y will also has to be transformed and your x will also has to be transformed. So you have to do the linear regression between log x and log y. Whatever intercept you will get is actually your log beta naught, and whatever slope you will get is nothing but your beta 1. Okay. So this is another. Next, the third one is when you have this kind of a feature where this is your zero. It's a logarithmic kind of a feature, you can see this, or you have something like this x y. This is zero y x. So if you have a relation like this, beta naught plus beta 1 log x, this is a relation. Okay, this is already linearized, so you can see. So it is between log x and y. You can do the simple linear fitting. And the last one, so before stopping, this is the last one which you have between x and y. This is also between x and y. And this is how the plots looks like this, whatever you have. You generally have a relation. This kind of relation is written like this: x divided by beta naught x minus beta 1. In this case, you can still use linearization, linear fitting by reciprocating it. So beta naught x minus beta 1 divided by x. So can be written as beta naught minus 1 by x beta 1. So now your y dash is equal to beta naught minus x dash beta 1. So now you have to do regression between 1 by y and 1 by x. Okay, so this is how you can change or transform any given function or fitting into a linearized, and then you do the linearization, simple linear regression model, and finally get the answer of the slope and the regression. So that's all for today. I think this is enough. Okay. So just try to quickly recap what I have done today. So these are all the assignment questions which I have shown. And once this is done, some practice questions we have done. And then we have started this week 8 content where we have found out the leverage point, how to get. We earlier know that HII, if it is very large, then that is a leverage point. But finally, there is a criterion which we can introduce, that is using K by N. If HII is greater than 2K by N, we call that as a outlier or a leverage point. We have seen an example of that. And then influential observation, which has the unusual x and y coordinate. We have seen Cook statistic as one of the tests for influential observation. Then we have seen DF fits, where we have found out that if the number of observations is n, then there will be n DF fit statistics. Whichever is larger, and particularly following this criteria, is the uh, influential observation. Next is DF betas, where you have also considering the regression coefficients. So both observation and regression coefficients together is multiplied. That many DF betas will be generated for computation, and then we have done a question corresponding to that. This is press statistic, and then some transformations related thing, which will be continuing in the week 9 for sure. So this everything is based on, we have always assumed that epsilon I is a normal distribution with 0 and sigma square. But sometimes what happens is that based on our data, we find that this assumption is not valid. That is, variance of epsilon I is not equal to sigma square. But if we know that this sigma square is proportional to mu, in some way it is related to mu, so k into mu to the power q, if this kind of thing happens, then we can derive or transform the y into some functions so that we can create the variance to be constant. And this is what everything is done for that. We have listed when this kind of things happens. And also we have seen when you have a particular kind of fit, then you can linearize those fits, like the exponential fits, you can linearize into simple linear regression model. Then this kind of a fit, okay, beta naught x to the power beta 1, this kind of a fit, this can be linearized. Okay, so these are the concepts of week 8. So I think whatever questions we have discussed, practice questions in between, those are important, and you can find that these questions may help you to solve the assignment. Assignment 8 questions. Okay, so we will discuss the assignment 8 in the next week. Okay, fine. With this, I wanted to end. If you don't have any question, any questions from? Okay, fine. Thank you.